You know, when I first heard about the multiverse, I thought it was crazy. I really did. It sounded like science fiction. It sounded like something you'd read in a comic book. But here's the thing. Sometimes the universe, or I should say the multiverse, is stranger than we could have ever imagined. And sometimes the craziest sounding idea turns out to be the only explanation that actually makes sense. So let me tell you why I think the multiverse is real. And I'm going to start with a problem. A really serious problem that kept me up at night for years. It's called the fine-tuning problem. Look around you, you're made of atoms. Those atoms are made of protons, neutrons, electrons. Those particles interact through forces, gravity, electromagnetism, the strong nuclear force, the weak nuclear force. Each of these forces has a strength. And here's what's bizarre. If you changed any of these strengths by just a tiny amount, we wouldn't be here. Life wouldn't exist. The universe would be completely sterile. Let me give you an example. The cosmological constant. This is the energy of empty space itself. Now, when we calculate what this number should be using quantum field theory, we get a number that's huge, absolutely enormous. But when we measure it, when we look at how the universe is actually expanding, we find that the cosmological constant is almost zero. Not exactly zero, that would be one thing, but almost zero. It's like 1 part in 10 to the power of 122. Let me put that in perspective. That's 1 followed by 122 zeros. That's not a million. That's not a billion. That's not even a number we have a name for in everyday language. The number of particles in the entire observable universe is about 10 to the 85. This is vastly, vastly smaller than that. Now, why does this matter? Because if the cosmological constant were much bigger, and I mean if it were just 10 to the 100th times bigger, which sounds like a lot, but remember, we're talking about 10 to the 122. If it were that much bigger, the universe would have expanded so fast that galaxies never would have formed. Stars never would have formed. You, me, everything we see, none of it would exist. And if it were negative by a similar amount, the universe would have collapsed back in on itself almost immediately after the Big Bang. Again, no galaxies, no stars, no us. So here we are sitting on a knife edge. The cosmological constant is tuned to an absurd precision, and this isn't the only constant. The strength of the strong nuclear force, if you changed that by 0.5%, carbon couldn't form. No carbon, no organic chemistry, no life. The mass of the electron relative to the mass of the proton, change that a little bit and chemistry doesn't work. Atoms fall apart or don't form the right way. Every direction you look, the universe appears to be exquisitely fine-tuned for our existence. Now, this is deeply troubling if you're a physicist. We don't like special conditions. We want to understand why things are the way they are from fundamental principles, not just accept that they happen to be perfectly suited for us. For a long time, people proposed all sorts of solutions. Maybe there's some deep principle we don't understand yet that forces these constants to have the values they have. Maybe there's a beautiful, elegant equation that we haven't discovered that explains everything. We kept looking, and we kept not finding it. Then along comes string theory. Now, string theory is this idea that the fundamental constituents of nature aren't point particles, but tiny vibrating strings. Different vibrations correspond to different particles. One vibration is an electron, another is a quark, another is a photon. It's a beautiful idea. It promised to unify all the forces of nature. A lot of us got very excited about it. But then we discovered something. String theory doesn't give you one universe. It doesn't give you one set of physical laws. When you work out the mathematics, and this took years to understand, you find that there are an enormous number of possible solutions. We call this the landscape. How many solutions? Well, conservative estimates put it at 10 to the 500. That's 10 to the power of 500 different possible universes, each with different values for the constants of nature, different particles, different forces, different laws of physics. At first, this seemed like a disaster. We wanted string theory to predict one universe, our universe. Instead, it was giving us this vast landscape of possibilities. Many of my colleagues hated this. They thought it meant string theory had failed. But then I started thinking about this differently. What if this wasn't a bug? What if it was a feature? You see, there was another development happening in cosmology around the same time. It's called eternal inflation. The basic idea is this. We know the universe inflated very rapidly right after the Big Bang. That's well established. But in eternal inflation, this process doesn't just happen once and stop everywhere. Space is constantly inflating in most places, and occasionally in little regions, inflation stops, and a universe, what we would call a universe, forms. These little regions where inflation stops are called bubble universes. And here's the key point. Each bubble can have different physics. When inflation stops in a particular region, the fields settle down into one of these possible vacuum states from the string theory landscape. One bubble might have one cosmological constant, another bubble might have a different one. One might have strong nuclear forces of a certain strength, another might be different. If this is true, and more, this is looking like it might be the way things actually are, then we live in a multiverse, a vast, possibly infinite collection of bubble universes, each with its own physics, its own constants, its own laws. Now, in most of those universes, the cosmological constant is huge. Galaxies don't form, or it's hugely negative, and the universe collapses, or the strong force is too strong, and all matter collapses into black holes, or it's too weak, and atomic nuclei fall apart. Most of those universes are sterile, dead, completely inhospitable to any form of complexity, let alone life. But in this vast multiverse, out of 10 to the 500 or more possibilities, there will be some rare, incredibly rare universes where the conditions happen to be just right, where the cosmological constant happens to be tiny, where the forces happen to have the right strengths, where galaxies can form, where stars can form, where planets can form, where chemistry works, where life can emerge. And obviously, we find ourselves in one of those universes. We have to. There's no other place we could be. This is sometimes called the Anthropic principle, but I don't like that name because it sounds like it's putting humans at the center of things, and that's not what this is about. It's just basic logic. Observers can only exist in universes that permit observers to exist. Think of it this way. Imagine you're walking along the beach and you find a beautiful, perfect seashell. You might think, wow, what are the odds? This shell is so perfect, so intricate, something must have designed it. But then you realize you walked past thousands of broken shells to get here. You didn't notice them because they weren't interesting. The beach is littered with shells, and you picked up the pretty one. That's what we're doing in the multiverse. We're the ones who can only exist where the conditions are right. Now, I know what you're thinking. This sounds like we're giving up. It sounds like we're saying, well, we can't explain these numbers, so let's just invoke an infinite number of universes and say we got lucky. I understand that objection. I really do. Some of my best friends in physics hate this idea for exactly that reason. But here's why I think they're wrong. We're not just making this up to solve a problem. String theory gives us the landscape. We didn't invent it to solve fine-tuning. Eternal inflation gives us the multiverse. We didn't invent it to solve fine-tuning. These ideas came from totally different considerations, from trying to understand quantum gravity and cosmology. The fact that they come together to solve the fine-tuning problem is actually evidence that we're on the right track. Let me give you an analogy. Before Darwin, people looked at the complexity of life and said, this is so intricate, so well designed, there must be a designer. It seemed obvious. But then Darwin showed us natural selection. Random variation plus selection over billions of years can produce all this complexity without any designer. At first, people resisted this. It seemed too random, too undirected, but it turned out to be true. The multiverse is similar. Instead of one universe designed for life, you have a vast landscape of possibilities, and we happen to find ourselves in one that works. It's not design, it's just statistics on a cosmic scale. And there's something else. The multiverse makes predictions. Steven Weinberg, one of the great physicists of the 20th century, actually used anthropic reasoning with the multiverse to predict the cosmological constant before it was measured. He said, look, if we're in a multiverse, the cosmological constant in our universe should be small enough for galaxies to form, but probably not much smaller than that. And he calculated a range. Then, years later, astronomers measured it, and it was right in that range. That's a real prediction. That's not just philosophy. Now, can we ever prove the multiverse exists? Can we see these other universes? Probably not directly. They're causally disconnected from us. Light from one bubble universe can't reach another bubble universe because the space between them is inflating too fast. we're stuck in our bubble, but we might find indirect evidence. We might see patterns in the cosmic microwave background, the afterglow of the Big Bang, that suggest our bubble collided with another bubble early on. We might find that certain ratios of constants are more probable in the landscape and check whether our universe has those typical values. These are things people are actively working on. But even without direct evidence, I think the multiverse is the most reasonable explanation we have. The alternative is to say that our universe is special for no reason at all, that all these constants just happen to have exactly the values they need for life by pure coincidence, and that, to me, is harder to believe than the multiverse. I've spent my whole career trying to understand the fundamental laws of nature. I wanted to find that one beautiful equation that explains everything. And maybe someday we will. Maybe there's a deeper theory that predicts the landscape, that tells us why string theory is the way it is. I hope so. But right now, today, when I look at all the evidence, the landscape from string theory, eternal inflation from cosmology, the absurd fine-tuning of the constants, when I put it all together, the multiverse is the best answer we have. It's not the answer I wanted when I started my career. It's not as elegant as one perfect universe with one perfect equation. But science isn't about what we want to be true. It's about what actually is true. And I think what's actually true is that we live in one tiny corner of an enormous, possibly infinite multiverse. Most of it is hostile to life. Most of it is nothing like our universe. But here and there, in rare pockets, the conditions are right. And in those rare pockets, beings like us can emerge and ask questions like, why is the universe the way it is? The answer might be, it isn't. The multiverse is the way it is. And we're just in the part where we can exist to ask the question. That's why I think the multiverse is real, not because it's convenient, not because it's pretty, but because, as far as I can tell, it's the only explanation that actually makes sense of what we observe. And if that's true, if we really do live in a multiverse, then that's one of the most profound discoveries in the history of human thought. It completely changes how we think about our place in reality. We're not at the center of the universe. We're not even in the only universe. We're in one of countless universes, most of which are utterly unlike our own. And somehow, I find that even more magnificent than the alternative. The reality we're part of is vaster and stranger than we ever imagined. And that, to me, is what physics is all about, discovering just how vast and strange reality really is.